AI seminar series. Today we have with us our newest member of the Matrix AI Consortium, Dr. Panos Markopoulos, who is an associate professor and Margie and Bill Kless endowed professor with the Department of ECE and Computer Science. Dr. Panos' interests are in the areas of machine learning, data analysis, and adaptive signal processing. And his primary research mission is to advance efficient, explainable, and trustworthy AI. He has published in several journal and conference articles, close to 70 of them, and he has been funded by sponsors such as National Science Foundation, National Geospatial Intelligence Agency, and the Air Force Office of Scientific Research. He also received the Air Force Young Investigator Program Award in 2019. It's an honor to have him here today with us, and we are really looking forward to his insights on tensor methods for machine learning. The floor is yours, Panos.
Thank you very much, Teresa. I'm very happy to be here, and thank you everyone for attending my talk today. So my talk will be on tensor methods for efficient, robust, and continual machine learning. A few words about myself, as I'm a new member of the UTSA community and the newest member in Matrix AI. So my full name is Panagiotis. You can call me Panos. I'm a new faculty member with ECE CS, the School of Data Science in Matrix AI. Originally, I come from Athens, Greece. Before joining UTSA this year, I was with RIT in Rochester, New York. My research is on machine learning, theory and algorithms, neural networks, tensor methods, corrupted and limited training data, and signal processing. And as Teresa said, I have been very thankful to be awarded with funds from NSF, AFOSR, FRL, and NGA for my research. Also, as I'm a new faculty at UTSA, I'm looking for new collaborations and students to join my team. So if you're interested, if whatever I talk about sounds interesting to you and you'd like to work with me, please feel free to send me an email. So this is a brief outline of the presentation. I will give first a brief introduction to tensors. I will talk about tensor factorization, and then I will get into some implementations of tensors in deep learning in neural networks. Across many dimensions. So one dimension is using tensors for making neural networks more efficient. Another is using them for making them more robust. Another dimension is using tensor methods for being able to learn, to adapt the network capacity. And last, I will talk about using tensors for continual machine learning. At the end, I will wrap up the presentation with some concluding remarks. So just a disclaimer, this is not a comprehensive literature review. I'll just share with you some inspiring ideas about how tensors can improve deep learning, and also some recent work from my team. And all the presentation today will be at a higher level, and I will skip all the beautiful math details in the tensor methods. So getting into tensors. What is a tensor? So a tensor is a data structure that has multiple dimensions. So it generalizes vectors, which are just 1D arrays, and matrices, which are 2D arrays. So if you want to go to higher dimensions, then we call that tensor, right? It will look like a cube if it is in the 3 dimensions, or, in higher dimensions, it makes it a little tricky for us to represent on a slide or on a piece of paper. But essentially, an easy way to understand this is that when you have an order n tensor, then this means that to identify each and every entry of this tensor, you will need n indices, right? So n coordinates. So for a vector, you just need 1 coordinate, just the number of the element. For matrix, you need 2 coordinates, row and column. For an n-order tensor, you need n coordinates. All right, so this green object on the right is a 3-way tensor, and it can grow to bigger dimensions as the application needs. So why do we care about tensors? Tensors have been used extensively for representing data in this as higher order arrays. And this higher order data naturally can be found in many applications. For example, on the left-hand side, you will see a hyperspectral image, which naturally is structured as a 3D tensor, with the three coordinates representing spatial coordinates x and y, and frequency coordinate, right? And then a video, for example, a grayscale video can be represented as again as a three-way tensor, as an order 3 tensor. So you have x and y spatial coordinates, and then time frame as the third dimension. And then an RGB video can be represented now as a 4-dimensional tensor. I couldn't draw a 4-dimensional tensor, but I presented it as an array of 3-dimensional tensors, all right? So, and now the 4 dimensions are because you have 2 spatial dimensions, and then you have time frame, and then you have also the frequency, the color frequency, red, green, blue. Now, yes, tensors have been used a lot in modeling data, representing data, and processing data over the past couple of decades, more so. But a question is, why don't we just take the data, vectorize them, right, and then process them as vectors? I mean, an entry is an entry, and it doesn't really matter how you present it, one would say. This is partially true, but something important about tensors is that in the structure, there is already encoded information about correlations in the data. Let me give you this very simple example. So look at this RGB image here, which is an aerial image from the VEDA dataset. And on the right-hand side, I'm opening this as, as a 3-way tensor, right? And take a look at this. The same pixel across different neighboring frequencies is bound to have some correlation. Or neighboring pixels within the same frequency, again, are bound to have some correlation. So the structure itself, the way that these pixels were placed in neighboring position across any of the orders, any of the ways of this tensor, essentially captures there, encodes there, the correlation that naturally exists between these measurements. If you would vectorize that 3-way tensor as a vector, the entries would be the same, but this information about the correlation would be lost. And maybe you would be able to retrieve it if you had a great number of such measurements, and then by some statistical methods, you could retrieve those correlations. But why distort the structure, lose that information, and then try to retrieve it if you keep that structure and process the data in the natural tensor form? Actually, we see that this information, these correlations are leveraged, and in many cases, the performance is significantly improved. So this is the reason why we care to preserve data in their tensor form and process them as such. Giving you some examples now. So in general, data are naturally stored as tensors whenever you have measurements over multiple dimensions, if you wish. For example, if you have measurements across location and across frequency and across time, right? So whenever you change the sensing dimension, then you introduce a new dimension in your tensor of data, all right? I gave you a few simple examples before. You can think of many other examples. For example, you can look at graphs, and graphs have adjacency matrices, and the adjacency matrices, whether that's a social network or whatever that graph represents, might change across time. So if you collect now snapshots of these graph representations of these adjacency matrices across time, then you create a 3-way tensor naturally, right? And then you might have entities that are connected over more than one networks, right? So we might be connected on Twitter, but we can also be connected on LinkedIn. These are my Twitter network and my LinkedIn network are 2 different networks where I'm connected with different entities in these 2 networks. And then also that changes across time. So there you have right away, we have now a 4-way tensor capturing my connections across multiple social networks across time, all right? So this is a simple idea of how, when the sensors change and the sensor configurations change, you collect data that introduce new dimensions and increase the size, the dimensionality of your tensor. Now, tensors have been used to model data in many areas. I have here some examples. They have been used in data mining. They have been used in computer vision, obviously to model videos and images. They have been used in remote sensing, in signal processing, in biomedical data, in wireless communications, and machine learning. So talking about that, we will get into a few details when it comes to how we represent tensors and how we write them down, and a few notation and terminologies that will be helpful for our discussion later on. So starting with tensor anatomy, you know, a tensor, as we said, is a high order array, but if you look at this matrix here, you can easily see that it's nothing but a collection of vectors. And these vectors can be arranged across the columns or can be arranged across the rows. So there are more than one ways to express this matrix or two-way or order 2 tensor as a collection of order 1 tensors. Similarly, you have this three-way tensor represented as a collection of matrices across the frontal side or the lateral or the side, right? But also it's a collection of vectors across, again, all three ways. And now I have this, I created this earlier this year, so I'm using it because I like it. So a three-way tensor is basically a collection of matrices, right? So you can see, we can when I say tensor anatomy, we mean that the higher order tensor can be represented. It is essentially a structured collection of tensors of lower orders, all right, of all possible lower orders. So you see here three-way tensors as collections of columns across different ways. We call these columns fibers of the tensor, or as a collection of matrices across different ways. We call these matrices now slabs of the tensor. And obviously, a four-order tensor can be seen as a collection of three-way tensors, but also slabs, but also fibers, all right? So this is how it goes in higher dimensions. Now, as we extend from matrices to tensors, we have to extend also the tools that we had to deal with matrices. So when we had just matrices, we had our linear algebra, which we're familiar with. We have a vector-to-vector product, vector-to-matrix product, matrix-to-matrix product, and all these good operations, you know, tensor, norms, and traces, inverses of matrices, matrix decomposition, etc. So we have all those good things that we know about linear algebra. But the moment we extend from linear algebra, from matrices to tensors, then we have to extend our linear algebra to multilinear algebra, also known as tensor algebra. So tensor algebra is nothing but an increased toolbox that has inside everything you knew about linear algebra, but also a few more things, that a few more operations and notations that we use for tensors. For example, two additional operations we have in multilinear algebra is the Kronecker product and the Catril-Rao product. These are two products that extend the notion of matrix-to-matrix product into higher dimensions for tensors. And the interesting thing is that most of the tensor operations can be rewritten as matrix operations, but these operations are of higher order. So a product between a tensor and a matrix, in fact, can be written as the product between two matrices, but this is not a regular product anymore. It's a Kronecker product. Okay, so be able to work with all the linear algebra that we knew and just append to it, add to it few tensor operations like Kronecker and Catril-Rao products. We need to be able to, in a systematic way, transition from tensors back to matrices. And this transition from tensors to matrices, we call it flattening, we call it unfolding or matricization. And it is done by convention in a very specific systematic way so that we know that we all agree on what we mean when we say matricization, right? Because you see, I can take the entries of this tensor and rearrange them in a matrix in numerous possible ways. But so as to make sure we're talking about the same thing, there has been some conventions on how exactly you do matricization or flattening. And then once you do that, then I will show you how, for example, an operation between a tensor and a matrix can be rewritten as an operation between matrices. So you see we have a tensor X, which is an n-dimensional tensor, all right? So it has n ways. And then you have a matrix A. And I want to multiply this tensor X on its n lowercase mode with matrix A. So this is a tensor to matrix multiplication. How can we do that? So the notation, first of all, is this, and this means mode n tensor to matrix product. And the way to do that is essentially you take that matrix, you flatten it, fold it across its nth mode. Sorry, you take the tensor, you unfold it across its nth mode, you create a matrix, and then you just multiply, you just do matrix to matrix multiplication, and you get a new matrix, which then you can reshape back to its n dimensions, and that's the matrix, that's the tensor you were looking for. So you see, all I have to do is do the transition down to matrices and then do some operation of matrices, and I'm back to tensors. The reason I'm saying that is one of the reasons that even though, as you will see later on, tensors can bring outstandingly good results, one of the reasons that has limited, arguably, their adoption is the fact that people think they have to learn a new linear algebra from scratch. They have to buy a new book just as big as the linear algebra book and learn it from scratch. That's not true, right? So with a basic understanding of linear algebra, plus a few more tools like Kronecker products and categorical products, you can do tensor operations. All right, so now I'll show you the most basic tensor operation here, which is, as I said, the tensor to matrix product. But this time, I have a tensor and I'm multiplying it with three matrices. One across mode 1, one across mode 2, and one across mode 3. And this gives me a new tensor. And I'll show you here that, in principle, what holds true is that this new tensor, its mode 1, for example, unfolding, is equal to the mode 1 unfolding of the original tensor times one of those matrices times the Kronecker product of these two other matrices. So you see, that's what I mean when I say that the tensor operation is actually an operation between matrices, but involves higher order products, such as the Kronecker product. So that's with that. And then with matrices, typically we talk about matrix decomposition. It is a very common tool to decompose a matrix for all kinds of reasons, to find latent factors, to compress, to denoise. For so many reasons, we do matrix decomposition. And essentially, a low-rank matrix is a matrix that is reducible. So it might have many entries, but indeed you can recreate that matrix by combining some factors that additively have fewer entries than the whole matrix, right? So here's a simple example. Assume that you have this 1,000 by 1,000 matrix, which has 1 million entries. But assume that this matrix is low rank, it has rank 2. So it can be written as the product of two matrices. One is of size 1,000 by 2, and the other is of size 2 by 1,000, right? And if we multiply them, we get back A. Now, collectively, these two matrices have 2,000 plus 2,000 equals 4,000 entries. So 4,000 entries suffice to be combined into producing the 1 million entries that matrix A has. So with just 4,000 parameters, if you wish, plus a few computations, get back A. All right, so you can. It's a very easy way to trade off between storage and computation. Right, if you don't want to store all the entries of A, but you have sufficient computation power to do that multiplication right here, then just store the entries of B and the entries of C, and then whenever you need A, just multiply them, use it as you want to use it. All right, so this is the beauty of low rank matrices. And in practice, even though if you have a matrix of interest A that is not really low rank by itself, we know that in many cases you can just very well approximate it by a low rank matrix and then do the same thing, right? And these approximations of matrices as other matrices of lower rank that are very close can be in the form of singular value decomposition, eigenvalue decomposition, QR decomposition, and so many decompositions we have for matrices. Now, these things extend to tensors, and they extend to tensors in more than one ways. And we use these low-rank factorizations of tensors for whatever I will show later on in deep neural networks. So we have to have a very basic understanding of what we mean when we say we factorize a tensor. So similarly to the case of the matrix, when you have a tensor like A, in many cases you can exactly rewrite A as the product of tensorial objects of smaller dimensions, of smaller size. So look at this A matrix, for example, A tensor, for example. I'm assuming it can be written as a smaller tensor, basis on its mode 1, times a basis on its mode 2, and times another basis on its mode 3. This basis here will expand the dimensions of this small tensor, right? But the low rank nature of this and the redundancy in the entries of A is obvious. So this type of factorization, tensor A, smaller tensor G, the dimensions of which are later expanded by mode n products with matrices, called factorization. And it's one of the most common factorizations for tensors. Now, these have names. We call this G, we call it the core of the Tucker factorization. And these B's, we call them the bases. And the columns of B's, typically we call them factors. And these three numbers here, D1, D2, and D3, which are the dimensions of the core, this triplet now here is the rank, the Tucker rank of this tensor. So you see, the notion of rank for matrices, which is just a number, extends to more than one numbers when you go up to tensors, right? So the rank is 3 numbers here for this tensor. And essentially, what I'm saying here is that this tensor A can be written as a linear combination of all the outer products of the columns of these bases. So this basis has some columns, they are factors. This has some columns, and this has some columns. All these are factors. Take all the possible combinations of these, all the possible triplets among factors from these 3 bases, among columns of these 3 bases. And for every possible triplet, determine a weight, and then do this linear combination. This is exactly what you have here in this schematic. Mathematically, this is exactly what happens. All right. So all the possible combinations, linear combinations of all the possible outer products of these factors, of these multi-way factors. So just to get an idea, let's assume that this tensor A has dimensions 10 by 10 by 10. And then assume that this core has dimensions 2 by 2 by 2. Then A, then A has 1,000 entries. G has 8 entries, and the remaining entries in B1, B2, and B3 altogether make 60 entries, 60 variables in this low rank expression. So instead of having 1,000 to store, you just have to store 60, as long as you can afford those multiplications between the factors and the core whenever you need to get back tensor A. Now, as I said before, if your tensor is not indeed of this structure, but it can be well approximated by a tensor of this structure, then we solve an optimization problem in which we try to find a core and basis so that this structure can fit as nicely, as tightly as possible to this tensor. Solving this optimization problem where we fit this tensor to this structure is called the Tucker decomposition. Essentially, we decompose, as we say, this tensor into a Tucker structure. And this decomposition might not be exact, right? If tensor A did not have, to begin with, this structure, then this decomposition will not be exact. You will have a loss. It will be a lossy operation. But in many cases, you can do this with a very low Tucker rank, and the loss is minuscule. And therefore, obviously, you have significant savings in storage. A variant of the Tucker decomposition is the parallel factor analysis. In the parallel factor analysis, it's pretty much the same thing, but you have a constraint on the entries of the core. The core cannot anymore be just any tensor of smaller size, but it has to be a tensor that is super diagonal. So every other entry other than the super diagonal, other than those entries that have 3 indices equal, every other entry has to be 0. And this is a constraint we impose on Tucker decomposition and gives us the parafact decomposition, the parallel factor analysis. So as the name says, we call this parallel factor analysis because when you take the inner products, the outer products now, between the factors of B1, the factors of B2, and the factors of B3, you can only combine factors that have the same column index in their corresponding matrices. So the first column here we only take the outer product of this first column with the first column of B2 and the first column of B3. We can never take the outer product of the first column with the second or the third, right? So across the columns, different factors become parallel in the sense that they never get combined because the weight that would be assigned to them is 0. So they never participate in the linear combination of the factorization, right? So you can see that the tensor decomposition, the Tucker decomposition with a general G, if you impose the constraint of the G is super diagonal, then you get the parafac, also known as canonical polyadic decomposition. It has two names. We can be using them interchangeably in this talk. So parafac and CPD are the same thing. So this is both of these different decompositions have been used extensively, but in different kind of problems. So the previous decomposition, the Tucker decomposition, is more so used when you want to just compress things, squeeze out the noise, and compress with the least possible loss. While this parallel factor analysis is used more so when you want to extract interpretable features. Obviously, when we operate in matrices, SVD does both. But when you operate on tensors, Tucker is more so for compression, parafac is more so for feature extraction. And the third decomposition I want to talk about, a third factorization, is the tensor train factorization, in which instead of expressing the tensor in a matrix tensor product, we express this tensor in a tensor to tensor product. So we express this tensor as the product of many tensors of smaller size. All right. I will not get into the mathematical details of how we do these products. As I said, I will skip the too much math for today because I want to get to some exciting applications. But just keep in mind that the tensor train factorization is the factorization of a tensor as a product of smaller tensors. And this is the notation, tensor train notation, all right? And now these smaller tensors, we call them cores of the tensor train factorization. Has been used in all kinds of different data. For example, in color, image, and video, in hyperspectral images, in functional MRI, in fMRI data, in EEG signals, in ECG signals, in social network graphs, in wireless communications, in genomic data. It has really been used in so many applications of science and engineering that are based on processing high order data. Okay. Now, if you want to learn more about tensor and tensor factorizations, I have three links here for you. The first one is a tutorial. The second one is a Python library for tensors. So you can be using it and just write your Python code and have all these tensor decompositions already there for you as functions to use. And the analogous for MATLAB is the third link. Now, let's get to the use of tensors for neural networks. And I'll be starting with using tensors for making neural networks more efficient. So when you have too many parameters to train in a neural network, we know that this typically leads to more things to store, more parameters to store, longer training time, longer inference time, because more parameters typically mean more operations. And also, you might have poor generalization if the number of parameters are too many with respect to the complexity of the underlying model you're looking for, the number of training data you have, or the noise in your data. So in general, you don't want to have too many parameters. You want to have just enough parameters to have a successful model. There have been many approaches to reduce the number of parameters from any model and adjust it to the needs of the application and to the needs of the data. Okay, so these approaches can be regularization approaches or pruning approaches. There have been multiple approaches in the literature over the past decade. So in this talk, I will be presenting ideas from the recent tensor literature that essentially try to reduce the number of parameters. And the two main dimensions across which the novelties that I will be present are network parameters as low-rank tensors. For example, modeling the fully connected layers or the convolutional filters as low-rank tensors. And the other dimension is introducing efficient tensor operations that could replace inner products and convolutions that you have in traditional neural networks. So the goals for doing that is to have storage savings, improve your training and inference times, improve your generalization, but also have adaptive capacity for the same architecture. And this is something we have been working on with my team, and accomplish continual learning, for which I will talk more about in the talk later. So first, let me start with what we call the tensor contraction layer. So the tensor contraction layer is a step taken to reduce the number of parameters needed to be trained for the fully connected layer at the end of a standard neural network. So consider that you have on the left-hand side the last activation tensor, which typically what we do with it is we vectorize it, and then we multiply it with the fully connected layer weights, which can be represented in the form of this matrix, in order to get the output. So this, as you can see, one thing that we did is we vectorized, and then we did a vector to matrix multiplication. And that's a typical fully connected layer. And as I said earlier in this talk, you vectorize a tensor and you process it as a vector as if you don't know anything about its prior tensor structure. You're losing something. You're discarding some information there, right? So a very simple idea says, just vectorizing this and processing it with a matrix as if this was always a vector, why don't you process it as if it was a tensor in its former tensor structure? And that is what is called the tensor contraction layer. So you'll take this activation tensor, and then instead of vectorizing and taking the inner product with the columns of this matrix, you will multiply it with three separate matrices on its three different ways. All right, you will process it as a tensor, essentially. And you will reduce its size significantly by means of this tensor contraction. And then after you reduce the size and you get a much smaller tensor here, then you can go ahead and vectorize it and process it with much fewer, this time, fully connected layer weights. All right, so you still have a fully connected layer, but now it operates on a much smaller tensor and a contracted version of your original tensor. And this contraction happened in a way that leverages the structure that this activation tensor originally had. And it has been shown, this was introduced back in 2017, and since then it has been extensively used. And this is the paper down here where this was introduced. And it has been shown that this can be very successful in both reducing the number of parameters that you store and performance, generalization performance. All right, so you have space savings, inference time savings, and often you can have also better generalization, essentially for the obvious reason of limiting the number of trainable parameters to better fit the application and data that you have. So in this paper that introduced this idea of tensor contraction layers, they use this method on ImageNet with a VGG, and they managed to attain 65.9% space savings, so reduction in the number of parameters, with a performance drop of just 0.6%. Now, what do I mean reduction? Let me just clarify this. I have color-coded my slides so that in all these schematics, the purple matrices and tensors are the ones to be trained. So you see now in the standard fully connected layer, what you have to train is this big matrix that contains the weights of the fully connected layer. Instead, in the tensor contraction layer, you have to train a much smaller fully connected layer matrix, and also the factors that will perform here, the multi-way contraction, the tensor contraction of your original activation tensor. So if you sum up together the number of parameters in these contraction matrices and the number of parameters in this the weights of the fully connected layer, the number you get is much smaller the number of parameters you had in this original fully connected layer matrix of weights. And yes, in this paper, they showed that they can reduce the number of parameters by 65.9% while attaining almost the same performance, right? Very close performance, 0.6%, just a reduction of just 0.6% of performance. And then using a different network, they were able to attain 56.6% savings with a performance improvement this time of 0.5%. So the performance is similar, a little less, a little more, but the savings in the space, in the number of parameters you store is just remarkable. Then one of my students, Mayur Dhanaraj, who has now graduated and is with Amazon, he did a paper last year collaborating with his Amazon colleagues in which he used tensor contraction layers for reducing the size of a network, the FBNet. But he did it in a special way, because the question, when you have to do a tensor contraction, when you choose to replace your fully connected layer with a tensor contraction layer, a question that comes to mind right away is how drastic should this contraction be? Like, how small do I want this tensor to be, right? So this obviously depends on the size of the contraction matrices that we're using in the tensor contraction here, all right? So what is the desirable size for this contraction matrices? And obviously that's a hyperparameter that you have to optimize by, maybe a validation data or by practice, etc. But Mayur here had an idea of how about I do an architecture search, a neural architecture search algorithm that can choose the dimension, the extent of the contraction in the tensor contraction layer. So by doing that, he managed to show that you can attain similar performance, right? So performance dropped from, let's say, 65 to 60 with a remarkable reduction in the number of parameters and the size of the model, right? And the natural architecture search algorithm he had was able to actually identify these contraction dimensions that give you the best performance. Okay, so that was the tensor contraction layer. And then there is another layer that was introduced in the paper Tensor Regression Networks in 2020, based on prior also work that was done in the previous few years. But this idea is called tensor regression layer. And the tensor regression layer does something different. Instead of me doing a tensor operation on the activation tensor, what I will do is I will assume that the fully connected layer weights are not a matrix, but they have a low Tucker rank. So instead of training the weights as a matrix, I will be training the latent factors, the latent Tucker factors in the core of the weights. And then as I'm training these, obviously, whenever I want to use them, I have two ways to go. One way to go is to, after I have trained this, I assemble them together into a tensor, I flatten the tensor, now I have a matrix, and then I vectorize the activation tensor, and I do a standard fully connected layer. Standard fully connected layer, but now the entries of the weight matrix have come through latent Tucker factors that you trained. And the other way to go, which is equivalent pretty much, is to just keep this in the tensor form that it had, combine what you trained into this yellow tensor, and then just do here a tensor contraction, okay? So this tensor contraction here basically is element-wise product of these two tensors and then sum it up. It's the same as if you had vectorized this times vectorized that, inner product with vectorized that, okay? So it's the same thing, but the main idea here is that we model the weights of the fully connected layer as a low rank Tucker tensor. This is called the tensor regression layer because obviously you're trying to fit now your data into a regression, looks like a regression model, but this has a Tucker structure. And you have trained a Tucker structure. So the authors of this paper used this tensor regression layer on ImageNet using the ResNet 101 And they managed to show that if you look at this point here, you can have savings of up to 70, almost 70, 68.2% in space in number of parameters, while the top 5% performance, or even the top 1% performance, they are pretty much the same. They change just in a very small extent, right? While if you want, you can have all the way to 92.4% space savings if you can afford something like a 4% drop in your top 5% accuracy. So you see, with a very small drop in the accuracy, you can actually have a model that have tremendously fewer parameters. Now, obviously, tensor contraction layers and tensor regression layers can be combined. You can do first tensor contraction and then take this tensor and again train your fully connected weights as a low rank tensor and then do tensor to tensor contraction here. And obviously you can combine the two. Okay. So in the tensor contraction, tensor regression layers, you can learn a low rank tensor manifold where both data and labels exist. You can have an addition, and this is really an additional type of regularization function, right? The fact that you, instead of going straight to the fully connected layer, you do the multi-way products essentially operate similar to how regularization would operate. And this gives you a compact network with fewer parameters and similar performance as we saw. But the natural questions here are, composition do you want to use? What kind of factorization do you want to use for your fully connected layer, right? For the matrix of weights, would it be Tucker, maybe Parafac, maybe tensor train? And there have been other approaches here. For example, another approach that uses tensor train. I'm citing here, and then in addition to what kind of approach, maybe what kind of rank, right? All these are questions that obviously are also hyperparameters and they're subject to optimization, practical optimization, okay? So you can customize this per your application, per your model, and the data you have. Now, I want to go to another topic, which is modeling. Instead of modeling the fully connected layer as a low rank tensor, now I will show you what has been proposed in the literature for modeling the convolutional filters as low rank tensors. So the convolution filter you see, naturally, it's a four-way tensor, okay, where X, Y, input channels, output channels, right? It's a four-way tensor. And typically when we train network, we do not make any assumptions on any structure, on any low rank structure for my convolution filters. We just train all the entries as a dense tensor. So this idea says, consider that your convolution filters can actually be well approximated as a tensor of lower rank, and instead of training all the entries of the filter as they are, instead train the latent factors of this low tensor structure. So train the cores and train the bases, train the factors of the low rank structure of your convolution filter. And then again, combine them together, combine these factors into the tensor of your convolution filter, and then do convolution basically just how you would do, right? So this is the idea. Now, one approach that has been widely used in the literature assumes that the structure of the convolutional filters is a low rank Parafac structure. The core is super diagonal. And another name for Parafac apart from CPD is Kruskal. So they also call this Kruskal convolution. So Kruskal convolutions are convolutions where the convolution filter actually has a low rank Parafac structure. That's what it is. All right. So instead of training your convolution filter, just train the factors of its Parafac structure. Now, what can you accomplish by doing that? If you have a network that has lots of convolutions, that most of the parameters are in the convolutions, in the convolution filters, then you can drastically decrease the number of parameters that you train. Because again, instead of doing this big convolution filter, you will just train the factors of its parafact structure. So you can reduce significantly the number of parameters with all the merits that this can have in terms of less storage, in terms of possibly better generalization, etc. In addition to that, we see that once you consider that the convolution filter has a low rank parafact structure, then convolution simplifies a sequence of to a sequence of convolutions across the different ways, across the different dimensions of the convolution filter. So you see, speaking, the moment that my convolution filter is has a parafact structure, and this U that you see here, these U are the factors of my parafact structure, then the output of the filter is just a multiplication of the input with these factors in a sequence, right? A sequence of multiplications of my input with these factors. And these multiplications actually happen serially, and we can interpret that they do the following. They decouple the convolutions across the different ways of the filter. So the first multiplication essentially will operate across the input channel and will do convolution only across the input channel. So it's a one-by-one convolution across the input channel. The second multiplication is a depth-wise, the third one is a depth-wise, and the third one is again one that happens across the output channel. It's a one-by-one convolution. So essentially, by assuming that, and this is the beauty of the parafact structure, particularly for this type of tensor, is that by assuming that your tensor has parafact structure, it simplifies the convolution, and also it gives you an opportunity to have an inner look in what exactly the convolution does by basically breaking it up into 4 steps. Okay, so convolutions were replaced by matrix of tensor products, and this is a parsimonious model as it saves parameters. And also it makes it clear what exactly you do with the factors on the input of the convolution filter. And this clarity in what happens there was used recently in an ISTATS paper in 2020 to actually work and derive theoretical generalization bounds for the convolution, right? So through its approximation, through its implementation as a cross-cal convolution. Okay, but obviously apart from parafact structure for the convolution filter, you can assume Tucker structure. And in this case, again, the convolution breaks into a sequence of products with the factors of the Tucker decomposition, but also with now the multiple different weights in the core of the Tucker decomposition. And essentially, again, now it breaks into 3 steps. One step is this one-by-one convolution, and then the convolution across X and Y happens jointly because now you have a core that is not super diagonal in the Tucker, and then the last one, extension to the output channels, happens again with one-by-one convolutions. And this is a similar approach that is used by ResNet bottleneck blocks, right? This one-by-one followed by a joint depth-wise, and then again one-by-one. All right, so and last we have the tensor train convolutions, where basically the convolution filter is assumed to have and trained as a low tensor train rank tensor. So we train now the tensor train cores. And for this, I want to show you a work that we did last year with one of my students, Manish Sharma, and collaborators, in which we took a YOLO type neural network, which the majority of the weights are in convolution filters used for object detection in aerial images. And we replaced all the convolution filters as low TT rank tensors, and we trained the tensor train rank, the tensor train cores. And then you can tune the extent of the compression by essentially tuning the size of those cores and the number of those cores. So we experimented with many different extents of compression and tried to see what happens in terms of results. So you see, the smaller this number, the more I compress, okay? So you see that as we increase, as we compress less, let's say, right? So as we increase the number of parameters, but we tune it by tuning the tensor train decomposition of the convolutional filters, the accuracy of detecting objects increases. And you see that the horizontal line is the accuracy of the YOLO RS network as it was, right? And you see that we can have 0.9% higher accuracy with 70% fewer parameters. So we get higher accuracy for much fewer parameters. Or we can have 9% higher accuracy with 20% fewer parameters. So in both cases, we generalize better, and we can have significant savings in terms of number of parameters used. And then we compare it also with EfficientDet, for example. EfficientDet has even fewer parameters than the proposed. Right, but has fewer parameters, but the performance is also less. Okay, so we have similar number of parameters, let's say to EfficientDet, a little more than EfficientDet, but we have higher performance. All right, so we can model. So now, one more thing I want to say is that we can model the parameters as tensors, as we said, whether that's fully connected layer or convolutional layer. But when do you do that? Do you first train them as they are, and then you do tensor decomposition, or do you train the factors? So far, I have been talking more so about training the factors, but in fact, you can do either. You can first train it as is, and then decompose the parameters, get the factors, and be using those factors for inference, or you can train those factors directly. Or you can do a combination, an iterative combination of the two. So you initialize or you download, ready initialize those factors, you decompose, and then you train again in the tensor form, and then you decompose again, and so on and so forth. Okay, one more thing I want to talk about is how you can robustify your neural networks using these tensor methods. So remember that CNNs can overfit to noisy training data. And when we say I want a more robust neural network, is a network that can generalize better even if it was trained with highly noisy data. And typically to robustify our networks, we do some kind of dropouts, right? So we drop some activations, or we randomly, right? Or we randomize the weights in a fully connected layer, and so on and so forth. But this can also be done in the low rank dimension, in the latent low rank dimension of the tensor decomposition, of the tensor factorization of your, let's say, convolutional filters. And this is what I'm showing here. This is the tensor dropout work that was published in 2021, where basically the convolution filters are trained as in their Kruskal format, so they have a perfect low rank structure, and then randomly, let's say with some Bernoulli distribution, you choose which of those factors to drop. All right, and you drop those factors. Essentially, you reduce the rank of your convolution filters. You reduce the tensor rank of them by dropping randomly some of the factors, and that's another way to do a dropout that facilitates robustness. And if your convolution filter was in a Tucker format, again, you can drop out some of the dimensions of the core, right, and the corresponding factors of the bases by this time sketching, using random sketching matrices that essentially reduce each of the dimensions of the core of the Tucker decomposition of your convolution filter. And if you do that, the authors in this paper showed that you can actually drop out all the way to 60% of your ranks, essentially of your factors, while maintaining, while even improving the top 5% or even the top 1% accuracy. And a similar result can be observed if the data are highly corrupted. So they use 3 different types of data corruption, and they show that again, dropping out tensor ranks can offer robustness. All right, and this is a figure that shows how the classification accuracy is maintained higher for a tensor dropout with 60%, so with probability of drop 0.6 is maintained much higher than just the standard model. Okay, one more work I want to talk about is how you can use tensors to adaptively change your network capacity. So consider that I have a convolutional neural network and consider that I'm having a tensor train factorization for the convolution filter. We did a work in which we do the following. We start with our network having low tensor train rank. So we have our convolutional filters have low tensor train rank. And therefore we have just limited parameters. And we avoid overfitting to the limited available training data we have. But as we keep collecting more training data, so this discussion is for how you can increase the number of parameters as more training data become available. So as we keep collecting more training data, we can be increasing the number of parameters of our network just by increasing the tensor train rank. So just by increasing the size of the tensor train cores of the convolutional filters. So this is a nice way to increase the capacity of your model, to increase the number of parameters of your model without changing its structure, just by changing the rank, just by changing the latent structure, right? So the cores of the low rank structure of your convolution filters. All right, so to demonstrate that, we consider the convolutional autoencoder of this particular type, and we chose a particular number of cores for the tensor train decomposition, and we tested it on the FNIST dataset. And we observed the following. We use two ways. We have two ways to increase the parameters. One way is the proposed way where we just increase the rank of the tensor train decomposition factorization of the convolutional filters. And the other way is by just adding more channels to my convolution, all right? Changing the network width, all right? So increasing the size of your convolutional filters by adding more channels to it. So you see that the proposed approach manages to attain higher image quality performance in the unseen data for much lower number of parameters. And now here I have a slide where I compare what happens if you just keep your capacity fixed versus increasing your capacity as more data become available. So you see, if you keep your capacity fixed, I'm assuming that I get a new stream of data every 300 epochs, right? So you keep getting more training data, but you have reached a plateau here because you do not have enough capacity to keep learning more from the new data that you collect. But if you increase the tensor train rank of the convolution filters as you collect more training data, then you can pass that plateau and actually manage to have a much better performance, right? So this is the importance of increasing your capacity when needed, when more training data are available. Okay, and the last thing I want to talk about today, and I apologize because I realize I'm 12 now, but I will be fast, is we want to show a method for continual learning with tensors. So in this case, what we do, continual learning means that you want to be learning new tasks without forgetting previous tasks. And of course, whenever you have a new task, you can always train a new dedicated network for this new task, but this is not practical, right? You cannot have a new network for its task. Somehow, you're going to learn the new task on top of the network that you used to learn the previous task, right? Somehow you want to be learning on top of one another. But in a way that you don't forget the previous tasks. And this has been studied a lot, and we have a lot to learn from how brains work also. But this approach, essentially, we do the following. We consider that our convolutional filter has a parafact structure, as I showed before. And every time that you want to learn a new task, essentially you increase the rank of the convolutional filters, and you train new factors on top of the previous ones. So you keep the previous factors that had learned the previous task, and on top of that, differentially, you add two new factors that learn what's different, essentially only what's different between the new task and the previous task. All right. So that's how you learn differentially on top of the previous task, but also in a parallel way because you do not touch at all the previous factors. So you learn parallelly, but in the latent domain of your parafact decomposition of the convolutional filters. And one thing that happens here, I compare what happens if you just have a new parallel network for each task. When you have, that's the green curve, The blue curve is when you have a new low rank network for its task. And the red curve, which you can't see, is what happens if you do the proposed and you keep increasing the rank as you go. So you see the number of parameters is the same with having one new parallel network with low rank, but the performance is outstandingly better with the proposed method. So the proposed method eliminates catastrophic forgetting and also gives you better performance for the same number of parameters as if you had parallel networks per task, parallel low rank networks per task. Okay, this is it. Concluding remarks. I will skip them for now, just hoping that we will have a few minutes to discuss. And I'll be here for as long as it's needed to have some interesting discussions. All right, so thank you very much for your attention.
Thank you, Panos, for a great introduction to tensors and how they can be applied for several applications in machine learning, including continual learning. The floor is open for questions. You can either unmute yourself and ask, or you can type in the chat. As we are getting in those questions, I think Anima's work that you presented right earlier on using the tensor contraction layer, I think that's what the first proposal came in, and then there was a tensor regression layer.
Yes, yes.
I haven't seen, or maybe I missed it during the presentation. Did you talk about what happens if I have the entire network rather than just this contraction layer? And what do you think would be the challenge if I have an end-to-end one in the tensor domain?
So there is just make sure I understand the question. So instead of having just the tensor contraction layer before the fully connected layer,
right?
You're asking what would happen if I would have similar contractions throughout the network,
yeah, because
right?
you mentioned that convolutions can, wherever you have higher number of convolutions, you can benefit from using these tensors in there, right? So,
Yes.
so why not in the earlier layers, or what is the reason that it was considered at the fully connected layer?
Yeah, so that's a very good question. So typically when we have for example, a convolution layer, a convolutional filter that has most of its parameters in the convolutions, it makes a big difference to assume that your convolutional filters have low rank. And we do that throughout the network. In my experiments, I have considered low rank for the convolution filters throughout the network, and I see significant merits. And I think that if you have a convolutional filter, it works quite nicely to model your filter as a low rank, rather to introduce in between convolutional filters tensor contraction layer, which I'm not saying it wouldn't work nicely. Maybe it also works nicely, but just don't have enough experience practicing with that. So I prefer to just model the convolutional filters as low-rank tensors. But in the case where you have networks where most of the parameters are on the fully connected layer at the end, then obviously you have a great merit if you process there this activation tensor, not with a full matrix, but with this tensor contraction layer. And just a point now that you mentioned that there is that I want to make is that when you process in the multi-way products with tensor contraction layer here, it's essentially quite similar to vectorizing this and processing it with a matrix for a fully connected layer, but that matrix is not dense. That matrix has a low Kronecker rank. So, yeah.
Okay, I see. Other questions? Claire? We have some of our faculty joining, I think.
I have a question. Can I ask?
Sure, go ahead.
Okay. Yes. So thank you. First of all, the presentation was very good. And I had one question regarding tensor contraction. So basically, if you are using it in MRI imaging, right? Because you can apply the MRI imaging, right? So you said that one of the advantage of tensor regression is that it reduces the number of parameters required. So I'm pretty sure there might be an effect of noise. How do you measure the performance? Do you measure by signal to noise ratio? Because that's what we usually use when we try to do image analysis and MRI. So do you think reducing the number of parameters might contribute to the noise? Did I make sense with my question?
I think I understand what you're saying. So in the case where you're trying basically to reconstruct an image, right?
Yes.
And the visual quality matters. Yeah, reducing the number of parameters might be a good thing, right? Especially if your input image is noisy. Having many parameters essentially leads to overfitting to those noisy measurements. So you essentially also capture the noise, but with a lower rank parameters, essentially you capture what's constant across your data. So not the noise necessarily, but the underlying information. So I'm optimistic that this would also work for MRI data.
Thank you.
Thank you for the question.
Okay. I think, was it Claire or somebody else had a question? The other part that you mentioned was the savings that this early work has shown, like, 68% space savings or
Yes.
90% space savings. I think that's really powerful result, right? Like to have that much amount of space saved. But is there any overhead? I mean, I didn't see like what is the kind of the caveat of using these, right? This is a great advantage. And I would want to have these in most of my networks if possible to save that much space. What is the caveat here?
So essentially what happens is that you're having these savings because you assume that this fully connected layer at the end, that this matrix has a low rank structure. So as long as this assumption does not limit your performance, because sometimes your data set is good and there's not much noise, you have enough training data, and reducing the number of parameters will limit your performance, possibly significantly. It didn't show in these examples here, but yeah, I wouldn't say that it's always safe to reduce aggressively the number of parameters. Sometimes you might have a significant performance drop, but otherwise, even computationally speaking, you have fewer computations, and storage-wise, you have fewer computations. So, yeah, I think that when your data needed, then reducing the parameters, like in this way, is beneficial. I cannot think of any, like if the data needed, right? I cannot think of any major disadvantage. Might be missing something though.
Okay. But in general, I think your takeaway, if I understand it correctly, is that certain types of data could benefit, right? Not necessarily.
Yes. Exactly.
And those are the examples you've given earlier. For simpler data, I think it's an overkill to use this.
Yes, exactly. Certain data can benefit, but in other cases, you might have a performance drop, actually.
Right. Okay, other questions for Panos? If not, I think you can reach him at the email. The email is listed right here on the slide.
Yes, please.
Other questions? Yeah, I know it's a lot of beneficial information and like full-blown tutorial as well on Tensor. So you can absorb this. The presentation will be available on YouTube, and then feel free to reach out to Panos with further questions. Thank you so much for your time and sharing your research with us today, Panos.
Thank you very much. It was a pleasure. Thank you for having me.
Bye.
Bye-bye.